We tend to think the ultimate boundary on artificial intelligence is computational power, having enough advanced chips to process the data. But the actual bottleneck is raw electricity. Data centers require massive, constant amounts of power to run. Industry leaders are making this explicit. OpenAI CEO Sam Altman recently testified before the Senate, stating that the sheer volume of AI we can deploy will be entirely dictated by the volume of energy we can generate to support it. You might assume solar and wind farms could fill this gap. The problem is that AI data centers operate 24 hours a day, 7 days a week, and require a constant, unbroken flow of electricity, a profile that intermittent renewables cannot match when the sun sets or the wind dies down. Building traditional, constant power sources isn't fast enough. A new nuclear plant often takes over a decade to construct, and large-scale natural gas projects are facing severe supply chain delays that push their start dates past 2029. Without a power source that is clean, constant, and capable of being built almost immediately, the AI industry hits a hard limit on its growth. A viable alternative is currently scaling up: Enhanced Geothermal Systems, or EGS, which are engineered underground reservoirs that extract the Earth's natural heat, can now deploy gigawatt-level power in under 3 years. A gigawatt is a massive unit of power, roughly equivalent to the output of a large nuclear reactor. Building these facilities requires a remarkably small physical footprint. On a per-megawatt basis, with a single megawatt enough to power a few hundred homes, EGS requires nearly 9 times less land than a solar farm. This map shows the geothermal potential and attractiveness across the United States. The dark blue regions indicate highly accessible resources, proving there is enough geothermal capacity to support massive data center clusters across 22 different states. The ideal energy solution for the most advanced technology in the world has been sitting right beneath our feet. Ironically, the mechanism that makes this clean energy feasible was perfected by the fossil fuel industry. EGS relies heavily on modern horizontal drilling. This diagram shows a geothermal doublet. Cold water is pumped down an injection well and forced through horizontal fractures in the hot rock. Absorbing extreme heat, it travels up a production well to a heat exchanger, spinning a turbine that sends electricity to the grid. Because all the water is re-injected, this creates a closed-loop cycle with zero water loss, allowing engineers to construct a reliable geothermal hotspot almost anywhere. Developers like Fervo Energy are optimizing this process through a technique called bench development. Instead of building separate surface facilities for every well, they drill multiple horizontal wells branching out from a single central location. By sharing the same surface infrastructure, this bench technique extracts up to 5 times more energy from the exact same plot of land. Pushing this technology even further means digging deeper into the Earth's crust, where temperatures can exceed 400 degrees Celsius. At that depth, standard physical drill bits melt and break against super-hot granite and basalt. To achieve grid-scale energy outputs, developers have to figure out how to bore through basement rock without using physical drill bits at all. Quace Energy is bypassing mechanical drilling entirely by using millimeter wave technology, originally pioneered in fusion research labs at the Massachusetts Institute of Technology. They use a device called a Gyrotron, which generates high-power electromagnetic waves to shoot a concentrated energy beam down the shaft. This beam completely vaporizes the hard rock, turning solid granite into ash. Reaching rock that hot means a single geothermal well can produce drastically more energy, allowing these plants to rival the output of massive fossil fuel facilities. Capital is flowing rapidly into these solutions. The Department of Energy has injected hundreds of millions in federal funding, while developers have secured over $460 million in Series E capital, a late-stage round of private investment meant to quickly scale up proven technologies. In southwest Utah, a 500-megawatt geothermal project called Cape Station is currently under construction. This site will act as the physical anchor for a massive new enhanced geothermal data center corridor. Data centers require massive cooling systems, which usually consume millions of gallons of local freshwater. In this corridor, the geothermal plant's waste heat will drive absorption chillers, cooling units powered by excess heat instead of electricity, allowing the data centers to cool themselves without draining local water supplies. By guaranteeing massive, continuous energy contracts, the AI industry is providing the exact financial demand needed to scale geothermal operations and drive their costs down to compete with cheap natural gas. For most of history, humans have looked upward for clean energy, capturing the wind, the sun, and the rain. We are now pivoting to the immense latent energy stored deep inside the planet. Sustaining the most advanced synthetic brains humanity has ever built simply requires tapping into the primordial heat radiating silently beneath our boots.